Okay, so here are the notes for lesson 12, mole ratio on page 2. The coefficients in a chemical reaction indicate how many counting units, such as moles or atoms of each reactant combine, and how many counting units of each product are formed in a single reaction. Coefficients always refer to the number of units that are combining. Atoms, molecules, moles. We use moles the most. They do not refer to the masses. Mass is conserved in the reaction, but we cannot directly relate the masses of the reactants to the masses of each other or the products, and vice versa. Okay? You should have seen that in the POGL. So mole ratios are represented by the coefficients in a chemical equation, which show how many units of each substance must combine for the maximum amount of to form. I think that's to form, yay for grammar, the maximum amount of products, okay? You get these from a balanced chemical equation. So this is why we went over in the first workbook, how do we balance a chemical equation? And why do we balance it? For the law of conservation of mass. But we are also now going to use this to do mole to mole conversions, which is stoichiometry. Okay? Cool beans. So while I transition, please answer the guiding question at the bottom of page 2 and then turn to page 7. Okay, so we're going to look at not just how we use dimensional analysis for mole conversions using a balanced chemical equation, but also a BCA, or before change after table. These are a series of steps that you can reference as you're practicing, but I am going to give you examples as well. So, and we have 2 math examples. So the first one, we are going to look at the dimensional analysis process. So this is dimensional analysis, which means using units and fractions. So what you've been doing. On the next one, we will look at how do we use a BCA table. Okay. So for this first one, how many moles of magnesium oxide will be produced? So it's telling me I'm going to make magnesium oxide. If 5 moles of magnesium, so that's one of my magnesiums, is reacted with excess oxygen gas. So I could put states of matter, right? This is probably a solid. That's probably a solid because there's no liquid in there. Is this a balanced chemical equation? No, it is not. So before I can do any math with a chemical equation or any mole conversions, I have to balance it. So balancing this, I see I need another oxygen on this side. I could do atom inventory, but this one's kind of straightforward. And then I need a 2 here. So I have a 2:1:2 ratio. So once I have my balanced equation, so here's our first step. And this applies for BCA tables. So we need a balanced equation. My second step is to do a roadmap. Okay. So I'm going to do my roadmap. It gives me 5 moles of magnesium. And it asks me for moles of the magnesium oxide. So now I can do my third step, which is my train track method. And this follows the new mole map or stoich map that you guys just got from me. It is the middle part, okay? Where what you start with is on the far left and what you end with is on the far right. And in the middle is our mole ratio to change our substance, okay? So we do these because the two different substances. We're looking at two different substances. So, setting up my train tracks of 5 moles of magnesium, and I'm going to change that into moles of magnesium oxide. How in the past have we found the denominator? Disco, diagonal drag. So I'm going to drag these units diagonally. From the POGL that we did on pages 3 through 6, we saw that the mole to mole ratio is from our balanced equation up here. So I look at the coefficients in front of each compound. If there is no coefficient, what do we assume that number is? 1. Good. And you can write it in. I won't take off points for that because, you know, you're not wrong. So what is my ratio for magnesium oxide to magnesium? 2 to 2, right? Because those are their coefficients. So in this case, the only thing that really changes is our units, because 2 over 2 is 1 over 1. So I have 5 moles of magnesium oxide. Okay? But this is showing the process, showing your work, because is it always going to be a 1-to-1 or 2-to-2 ratio? No. Okay? So then our fourth step is to solve. Okay, so here's another example. In this one, we are going to look at the BCA table. Okay, remember this is a before, change, and after. Okay, so we're going to look at that sort of process. But for everything, in order to do a stoichiometric calculation, which is what this is, we have to write a balanced chemical equation. I have like a hiccup trying to go, and I'm trying not to hiccup on the video. But now everybody knows I had a hiccup. So we need a balanced equation. So we have moles of methane combusting with excess oxygen. So we have CH4, and that's usually a gas, reacting with excess oxygen gas. Now, oxygen gas is usually O2. It's one of the diatomics. So when we see like oxygen or any of these, Hofbrinkel, when we see like hydrogen gas reacting, it actually means H2. We see oxygen gas, it means O2. Fluorine, bromine, iodine, nitrogen, and chlorine, those all follow the same process. So when we see nitrogen gas, it means N2. Bromide or bromine gas is usually liquid, but bromine, like elemental bromine, is Br2. These are diatomic elements, just to clarify a few things, because it's going to come up. So when we are reacting these, unless it explicitly gives you something different, assume that they come in a pair. And this is Hofbrinkel. You are free to write this on your periodic table. And I'll leave it up for a second so you can get it after. So let's get that after. Okay, if we are combusting stuff, what are the products for combustion? And H2O. Okay? If we pay attention, we notice that this is not balanced. To balance it, you could do atom inventory. Miss Bert's going to go a little fast. So I'm going to write a 2 here because we do oxygen last, and that brings hydrogen to 4. So I have 1 carbon on both sides, 4 hydrogens now on both sides, and then I have 2 plus 2 oxygen. That tells me I need a 2 here to have 4 total. Okay? So we have our balanced equation. Our second step then is to set up the BCA table. On BCA tables, you can only use moles. So if you are given grams, what do you think you need to do first? Change it to moles. If you are given liters, change it to moles. If you are given particles of any persuasion, change it to moles. BCA tables only work for moles because it is looking at the mole ratios. Okay, so we write BCA just to the left of where our reactions start, like where we started writing out our reaction. A line between the C and the A because there's a reason, and I'll show you, but draw a line between the C and the A. And we want to separate out all of our stuff. So I draw a single line under each plus sign and a double line under the arrow so I know where my reactants are and where my products are. So they are double separated. Okay? So this is setting up our BCA table. And the steps were earlier, but I'm walking you through them now. So you should see them on your thing. I'm outlining it here now. Okay. After you outline the table, you plug in what you know, what you are given. So it tells us that we produce 8 moles of water. Okay. So if we are starting with 8 moles of water, okay, so from this, usually we use BCA tables when we are given multiple quantities to start with, okay? In this case, we aren't, but that's okay because it's a very simplified example, and we'll do more complicated ones as we move through this section of the unit. So we are given 8 moles of water. Is water a reactant or a product? A product. So are we going to have water before our reaction starts or after? After. So we will fill in 8 here. We do not need, you can, but you do not need to use units in the BCA table because you only use moles in the BCA table. Okay? So, once we've set up the BCA table, we start filling in what we know. So we know after the reaction, we have 8 moles of water. Before the reaction, how much water do we have? 0. How much carbon dioxide? 0. Okay. It also tells us we have excess oxygen gas. Excess means we aren't going to consider it. We've got too much for it to matter. So you can X out anything that is excess. Ooh. Okay. After the reaction, if we assume it goes to completion, and because oxygen is in excess, we should have nothing left over. So once we've filled in everything, a thing to remember is that before we start our reaction, we have no products. After we finish our reaction and made everything, we should have no reactants. There are conditions where that will change, but for our starting with this, we assume before no product, after no reactant. Okay? So from this, we can use our coefficients to look at our changes. So for the C, we drag down our coefficients. My apologies. So the coefficient for methane is 1. Water, I crossed it off, but I would drag down a 2. Or not water, oxygen. Drag down a 2. Carbon dioxide's a 1, and water is a 2. You also have very specific signs associated with these. So for reactants, because you're using them, it's going to be negative because you're going to react them. Products is positive. And then we have our change. How much is it changing based off of our quantities? Okay. So the change uses the coefficients. The parentheses we're going to fill in where we only have one unknown. Notice I have two unknowns here, two unknowns here, two unknowns here. I only have one spot I don't know here. I can call this x temporarily and set up an algebraic expression. You ready? What is 0 plus 2x equal to 8? What's x? 4. So 2x is equal to 8. X is 4. And we can say, hey, let's use sig figs. So what goes in all of the parentheses? 4. The parentheses will always be the same. Good? Okay. Can we figure out all of our other values now? Yeah. 0 plus 4 is 4. Something minus 4 is 0. Well, that I hope is a little obvious. And then if we wanted to know anything about oxygen, this would be 8. So we use fairly straightforward algebra to fill in the spots. Now, are the numbers always going to be really nice like this? No. They're usually going to be less than 1 and in decimal form. But the coefficients will always be whole numbers to help you make this solving process a little easier. Going back to our question, it says how many moles of methane? Well, we go to methane. This is how many moles need to combust. So we say 4 moles of methane. And if you wanted to be super specific, you could say combust. And that is how we use a BCA table to do the same process. Now, here we go, is a solve and circle answers. These we're going to come back to after we do some practice. You have 4 questions. Hold on. So you'll do some practice, then answer the BCA table. And thank you for tuning in.